Hello everybody, so today I will talk about the system design of WhatsApp again, and I will talk about these deep dive topics. So I will start with the first one. What happens if the WebSocket connection fails? So I will talk about this part, this WebSocket connection. So typically in the WhatsApp, the app should keep the WebSocket connections while it is running. But let's say user closes the app in the smartphone, and in that case, unfortunately, typically, there isn't enough time to tell the client app to notify the server that it would like to finish the connection. So I have to think that client suddenly stops the connection. Terminates the connection. And also, of course, there are some similar cases, like let's say the user is using the app, but he's on the train and the train goes into the tunnel. In that case, it is possible that network connection is disrupted for a while. So in that case, in the same way, the WebSocket connection is failed. So I will talk how I can handle this. So in that case, what the server side can do is kind of sending the ping pong message, just like the heartbeat. So client should send the message to the server should send the message to the client, and if the client is still alive and connected, the client sends back the message. So server side, in this case, real-time message service server sends a ping, and then the client device sends back pong, ping pong way. And if the pong isn't replied, okay, let's say the server sends a message every 5 seconds, and if the message doesn't come back for maybe 10 seconds, the server considers that the client is now dead and disconnected, and deletes the WebSocket object sustained in the server side. So that's how this server releases the memory for this zombie WebSocket connection. Okay, and of course, when user comes back to the when the user's app is connected to the server again, the same thing happens as the first connection. So it's create a new WebSocket connection, and also, of course, this server creates the map. Add that item to the mapping. And also this server subscribes the Redis pub sub for this for that user. And of course, there are some messages which the client missed client couldn't receive because the WebSocket was disconnected. So when the device is connected to the server side, every time it hits receive past messages API to bulk fetch the past messages the device couldn't receive. Okay, so that's what happens when WebSocket connection fails. Okay, so now we're talking about the second topic. What happens if Redis fails to deliver a message? So I will talk about the case when this Redis pub-sub goes down. So in that case, how the client can notice the lost message and fetches the undelivered messages. So of course, the most naive way is the user hits the bulk fetch API of the messages, receive pass messages API periodically to fetch the messages. But of course, this has a kind of issue. So so short polling basically is very, server is very heavy loaded with the short polling because each client keeps calling the API again and again. So to mitigate this, we can make the frequency of the bulk fetch API call less frequent. But now the problem is the latency of the message. So let's say this, device calls the receive pass messages API every 1 minute. It is possible that in that case, if the message delivery fails, that message is delivered 59 seconds later. So that's a kind of big latency. So even though periodic bulk fetch API call approach works, the latency is so big with this. So I will still introduce some solutions to supplement this. So aside from the short polling, the way the approach I can take is, let's say every time user receives a message in the chat, he should check all the past messages are already received to that user. So that's something I can do. So for that, let's say user receives the message in some chat room. So what I can do is kind of assign the sequence number to the messages in the same chat. So let's say in the chat room A, the messages are, has the sequence number 1, 2, 3, 4, 5, 6, 7, blah, blah, blah. So when the client receives the message with sequence number 5, he checks all the messages until 5, which means 1, 2, 3, 4 are already delivered. And if not, the client can hit the bulk message, past message bulk fetch API to fetch missing messages. So for this, what I have to do is to add the sequential number to the messages in the same chat. And because this real-time message service servers are scaled out, it is possible that the messages in the same chat are, sequence number of the same chat should be incremented across multiple servers. So for that, I introduced the Redis distributed counter. So because Redis is single-threaded, this server has to increment the counter in the Redis and then gets the incremented current number. And because Redis is single-threaded, this sequential number for each chat should be incremented. I should say serializable way. Or I should say linearizable way. So I can say chat ID to current, I would say sig number. So this is stored in this counter, and when real-time message service server makes a request, this increments the chat ID's sequential number and return it. Then this real-time message service can attach the sequential number to the messages in the scope of the same chat. Okay, and this is returned to the user, and now, as I said, the client device can check the sequence number, and if the path number is missing, it fetches the path ones with BulkFetch API. I have two things I'd like to call out. So firstly, the scalability about this Redis distributed counter. So I can use the Redis cluster and scale out, and I can use the chat ID as the partition key, because what it does is just a simple counter. So it is totally fine that I scale out by with the partition key chat ID. And another thing I'd like to mention is, what if this Redis distributed counter fails? In that case, what happens is that the message cannot assign the sequence number. I think this is acceptable. I can make this, API call, the best effort. So I said it is very good if the client receives a message, and if there is a message in the past which is missing, the client should notice it. But I think I would like to make this best effort. So which means that if this Redis distributed counter is dead, the sequence number is not assigned to the message, but I accept it. When this Redis distributed counter comes back, we can start from the number, which is definitely, let's just say, maybe I can do it in this way. So maybe I assign this like 112 or something. Oh no, wait, how can I do it? So what I can do is, okay, let's assign the same number, from the past. So it is possible that there are some messages which are, which were generated by users while this Redis distributed counter is down. But even with that, I start the counter from the past number, which was before this Redis counter went down. So in that case, client side may miss some numbers, miss some messages which are sent, delivered, while this Redis distributed counter is down. But still, I'd like to make it best effort. So after this comes back, we can, the client device can notice the missing messages. Okay, so I will quickly write it here. So number one, so I said show the polling of BulkFetch API call. And I said another solution which is combined with the first one is sequence number on messages in the chat. But still, there is a case that the delivery of the message has big latency, high latency. So I can say, let's say, how should I say? So okay, so we can notice if the message is missing. Let's say there is a message which is not delivered in the specific chat. We cannot notice it immediately. The client doesn't notice it immediately. But when the next message comes, when the next message is delivered, the client can notice the missing message. So which means that if the message is delivered, but it failed, and there is no new message, the client cannot notice the message. So I will add another layer of the mechanism to notice that the message is missing. So there is sequence number on messages in the same user. So this is per user level sequence number on the messages. So let's say okay, I assign the sequential number to the messages of the same user, and as I said, we do in the last discussion for this one, WebSocket connection failure, I told that this real-time message service server sends a heartbeat to the client device to confirm that the WebSocket is still alive. So I will make use of this. So when real-time message service sends that ping pong message, it includes the latest sequence ID which should have been sent to that user or the device. So actually this should be device. Yeah, but per device if I introduce the device level, messaging. But because I wrote it here as the user, I use the user, level. User, yeah. So that's the thing. So what I can do is, but now the thing is, this per user sequence number should be attached to here, message delivery. So this means that, okay, yeah. No, wait a minute. Okay, so what I can do is actually this message sequence number on the message doesn't have to be persisted in the database. So what I can do is when the message comes to this real-time message service, it pushes it to the Redis PubSub. And before that, let's say there are 10 people in the same chat room. This real-time message service hits the Redis distributed counter. And for user ID, I put the sequence number, I save the sequence number in the Redis distributed counter in the similar way, in the same way as chat ID. Of course, they don't have to be in the same Redis database. It's okay that we separate them. But the same thing can be said in terms of the scalability, because this is per user ID management. We can use the Redis cluster and partition by user ID. It is completely possible. And now real-time message service hits this counter to get the next sequence number for the message for that user, for each user, and yeah, included in the message. Yeah. And the message is sent to the user through Redis PubSub. Oh, wait a minute. So maybe, sorry, let me change a little bit of the design. So instead of issuing the sequence number before pushing it publishing the message to the Redis pub/sub, I'd rather issue the sequence number for the message immediately before sending the message to the user through WebSocket. So after this real-time message service receives the message from Redis pub/sub, this hits the Redis distributed counter to get the latest sequence number for the message in that user, and then attach it to the message. And of course, as I said, we have to store, the pinball message. Okay, so when this real-time message service server does the heartbeat to the user, this fetches the latest sequence number of that user and include it into the heartbeat. In this way, user can notice if the sequence number specified in the heartbeat is equal to the latest message that user has received with the WebSocket connection. If they're the same, it's okay. This client has called up on the latest message. But if they're not the same, or I should say, the latest message this client has received through WebSocket, that sequence number is less than the sequence number specified in the heartbeat. It means that the client has to fetch the past missing messages. So now this client calls the bulk fetch past messages API. Yeah. So that's what happens. Okay, so I quickly summarize. So to handle the case when Redis fails, oh sorry, I was talking about this. So how to fetch messages which the Redis failed to deliver. Yeah, I was talking about this. So this client, sorry, we use these three layers. Oh, sorry, so actually these two things are saying the same thing. So I read only this one. What happens if Redis fails to deliver a message? So, okay, wait a minute. So, what happens if Redis fails to deliver a message? Okay, so the answer of this is, sorry, I was a bit confused. So, the answer of this is the client uses the bulk fetch past message bulk fetch API. And what I discussed is how the client can notice the past missing messages. And if the Redis failed to deliver a message, okay, so in that case, the client can notice the missing messages, the failure of the delivery of the messages in the mechanism I mentioned, and then fetches past messages with bulk fetch API. Okay, and the mechanism for the client to notice the missing messages are these three layered approach. Short polling of bulk fetch API, and also sequence number of the messages in the chat, and sequence number of messages in the user. Just to be clear, this can be, let's say, every 1 minute. Yeah, of course, I cannot make this too frequent because it heavy loads the server. And for the second one, the timing that this is kind of triggered is when the latest message arrives. But of course, as I said, what I can notice with this is when the message arrives in the chat, so the client can notice the missing messages in the same chat only, and also if the latest message failed to be delivered, the client can notice it. And for the third one, this client can notice this when the hit heartbeat message arrives from the server. Yeah. So this is around every 10 sec. Yeah. So in the worst case, if this number 3 layer is working, the client can notice the missing message after 10 seconds. Okay, so this is it. And yeah. Okay. The reason why I still remain this number 1 is because even if the WebSocket fails, it is possible that even if the WebSocket is failed and dead, HTTP connection, HTTP request, only HTTP request works in some cases. So that's why I, keep this number 1 layer. Okay, so next I will talk about this topic. How do we handle out of order messages? So out of order messages means that as a message arrives to the client out of order, which means that let's say a user sends a message A first and then B next, but the receiver receives it B first and then A next. So in that case, what I can do is sort the messages in the front end according to the timestamp of the message. And the problem appears now how we can decide the timestamp of the message. So I can set it as so what we can do is this real-time message service server puts the timestamp to the message when the message arrives. And of course, there is a problem that in a distributed system, the timestamp created by the server may not be exactly, ordered in the real timestamp because there's a kind of small glitch in the clock of each server. So I will handle it with the best effort. So I use the kind of network time protocol to adjust the clock in each server as the best effort. And actually this network time protocol is, for example, in AWS EC2, this comes natively with EC2 servers. So we don't have to implement this network time protocol as long as we use AWS EC2, for example. Yeah. And that being said, I just call out that in the UX, it is possible that, let's say, the first message B arrives first, and then message A arrives next. So in this case, message A is inserted into the message, inserted above message B. So I think this is acceptable. Of course, this is a product decision. So, but yeah, I think it isn't a big issue. Because as I said, in most cases this doesn't happen, and even if this happens, user just scrolls up to, read back some messages. Yeah. Okay, so I will talk about the Rust topic. Rust seeing at functionality. Sorry, I was not clear. I talk about Rust online at functionality. So this is like the green, small dot, which is displayed on the user profile icon picture. And also we'd like to show if the user is online, but also if he's not online now, I'd like to show how many minutes ago he was online. And I would say the most naive approach is that when real-time message service sends a heartbeat to the user, and if the response is returned from the client, this real-time message service can update the database table, which includes the mapping, like for each user ID, last online at. So this real-time message service updates the online DB for that user, and then in this way, this last online ad is updated every 10 seconds for each user. And now when used in the front end, when it needs to show the last online status of his friends, of the user's friends, it fetches the user's last online ad timestamp from the backend and display it. And of course, if last online ad is less than 10 seconds before from the current timestamp, we can display that user as online. So that is the kind of naive approach, but there is a problem. So this online DB is updated for each user every 10 seconds. This is so heavy. Yeah. And also, it is possible that the network connection is, I would say, intermittent, and the connection is lost, intermittently. Let's say when user is in the tunnel in the train. So yeah, I think this approach is not scalable. So I will be more specific. So the problem here is not the actually DB write on the second thought. So yeah, so real-time message service server writes the online DB so frequently, but let's say we use the Redis and partition by user ID. In that case, it is possible to handle the write queries, which is executed on this Redis DB. But still, this client has to send the online status, let's say every 10 seconds, according to the product decision. And this is quite heavy loaded. Yeah. So probably we need another server here, which is to return the online status. And this reads from this table like this. So, but this is, yeah, so heavy loaded on this server. And also another problem is let's say there is a user whose connection is lost. It takes around, this interval until that that user becomes offline. So in some cases, this is good, and in some cases, this is not good. Let's say the polling is every, 20 seconds. Because this is a chat app, we'd like to send the message every, within 500 milliseconds. In this world, the online presence switching latency cannot be 10 seconds. So that's the problem I have here. So instead of that, what I can do is when the user is connected to the when the user is online, we notify that online status to other users with WebSocket. And when user is disconnected, we send that status update to other users with WebSocket too. So that's the kind of design I'm thinking now. So for this, what I can do is, let's say some user is connected to this server. Then we should notify other users who are in the same chat on the online presence of this user. Okay, so what I can do is, when the user is connected, then we publish that user's online presence change to the Redis PubSub. We can create another Redis PubSub topic for that purpose, and then that is propagated, or I should say published to other servers, and for other servers, the users who has to show that user's online presence, for those devices, the user one's online presence changes sent. And let's say user one becomes offline. This can be noticed with the web heartbeat check, or user one terminates the connection. So in that case, this real-time message service server observes the network termination, and in the same way, it is propagated to the other clients, and the client should delete the online presence. So with this approach, it seems like this Redis DB is not needed. But I have to think of the case. Let's say user 1 is connected to the server A, and user 2, the client device of the user 2 displays the user 1's online presence status. And let's say this server A goes down. In that case, we cannot notify user 2's device that user 1 became offline. So user 1's presence is still, keeps online in user 2's device. To avoid this, I include here Redis online DB, or I should say online Redis. Let's say present Redis, online present Redis, and I store only the online users' statuses. Yeah, so, and let's say Rust online add timestamp, and I set TTL like maybe 20 seconds, which should be longer than the heartbeat heartbeat interval. And if user 1 server A goes down, this user 1's record will not be updated anymore in this Redis. So with this TTL, it will be deleted after a while. And now, from the user 2's client device, it should hit a kind of online status bulk fetch API, which should be newly created API, which returns the online status, which is stored in this online presence Redis. So this API is used as a kind of fallback. Yeah. So client device, let's say, hits this API every 1 minute, and if the user 1, the client device of user 2 can notice that even though user 1's online presence is still online, it was thinking so, but when it looks at the kind of mapping returned from this online presence bulk fetch API, user one is missing. In that case, user two device can delete, let's just say, flip the user one's online status to offline. So yeah, that's the idea what I can do with this one. So I will repeat my idea. So as a kind of summary, so basically I use the Websocket to notify the online presence change from online to offline and also offline to online to other users. But it is possible that the user's connected server goes down. In that case, there is no way to notify other users that that user became offline. So for that, as a fallback, we use the online presence Redis server and store the last online timestamp of that each user. And with TTL, if this is not updated periodically, this record is deleted. So in this way, by the client calls the API to bulk fetch the online statuses for other users, we can handle the scenario that server goes down and user goes offline. Okay, so I finished talking about this topic. Yep. That being said, I finished my today's system design practice. Yeah, I will. Yeah, basically, on the first day, take one, my explanation is, as you can see, not so smooth, not so concise sometimes, but I do listen to the video, watch the video by myself, and tomorrow, as a take two, I will, explain this more concisely, hopefully. Okay, thank you so much. Bye.